Hello everyone. The topic of our project is the RSA public key crypto system. I am Saksham and Rishikesh is my partner for this project. Both of us are grad student in the Department of Computer Science at CU Boulder. So the outline of our presentation is as follows. First, we'll give a brief introduction of what RSA, the public key crypto system is. Then we'll talk about the fundamental principles of RSA. Further, we'll try to explore the practical applications of RSA. Later, we will see what are the potential threats to RSA. And finally, we will conclude. Let's begin with the introduction. So RSA stands for Reversed Shamir Alderman Public Key Crypto System. It is an asymmetric encryption algorithm, which means it uses two different keys for encryption and decryption processes. So basically, there are two types of encryption algorithms. One is symmetric encryption algorithm and the other is asymmetric encryption algorithm. What asymmetric encryption algorithm is, I just talked about, but in a symmetric encryption algorithm, a single key is used for both encryption and decryption process. Moving back to RSA, it is widely used for secure data transmission, digital signatures, and authentication in various applications, including SSL, TLS, email encryptions, and secure communication protocols. So, few of these examples we'll describe in the subsequent slides. Also, RSA security heavily lies on the difficulty of factoring large prime numbers. Now, a very high-level view of what RSA does is it uses a public key to encrypt data and uses a private key to decrypt the encrypted data. Moving to the principle of RSA, let's say we have a sender and a recipient. Now, a sender wants to send a message to the recipient without the message being compromised on the channel. So it wants to encrypt the data so that the data is secured and reaches securely to the recipient without any tampering or without the eavesdropper reading it also. So the sender has the data in the form of plain text. The sender will encrypt the data using the recipient's public key. After the data has been encrypted, the data will convert into a ciphertext form. Now, ciphertext is something gibberish. It is ununderstandable. So even if eavesdropper tries to read it, they might not be able to understand what it is all about. Now, as soon as the recipient receives the ciphertext, they will just use their private key to decrypt it and to get back the plain text message, which the sender was intending to send. So this is a very high level view of the principle for RSA. So the first step for the RSA algorithm is key generation. So we'll begin with choosing two different prime numbers, P and Q. Now P and Q, both of them are very large prime numbers. Next we compute N, which is product of the two prime numbers P and Q. Next we compute the Euler-Tocient function phi n, which is equal to P minus 1 into Q minus 1. Next we'll choose an integer E. Such that E lies in the range between 1 and phi n and is also co-prime to phi n, which means GCD of E and phi n equals to 1. Now E is basically the public exponent. I'll just talk about what exponent means in the subsequent slide. So, and then our next step will be to compute the value of D. So basically D into E is equal to 1 mod phi n, where D is equal to E in inverse and then modulo phi n, where D is basically the private exponent. So we get the public key as E comma n and private key as D comma n. Now let's talk about the encryption and decryption algorithm in RSA. So first let's talk about the symbols. So M is the plain text message which the sender is intending to send and the receiver is intending to receive. C is the ciphertext, which is basically the encrypted form of the plain text message. So the sender uses the recipient's public key E comma N to encrypt the message. So the sender will just encrypt the message using the recipient's public key. Now, and the encryption, the formula for encryption is C equals to m to the power e mod n. Now, the challenge with this encryption is that m is a plain text message. So, and this formula will not work on some alphanumerics. So, what the general rule is that we just convert this plain text message into numerical representation by using some encoding scheme such as ASCII or Unicode and like different custom schemes to get a numerical representation form. After we get the numerical representation form, we just apply this formula to get the ciphertext. Now the receiver receives this ciphertext C. Now the receiver will decrypt it using this formula. M is equal to C to the power D mod N. Now, but what initially the receiver will get M as a numerical represented form. So then the receiver will have to use the same encoding scheme which the sender has had used to convert the plain text into numerical representation. So the receiver will just use the ASCII or Unicode or whatever scheme was used, and he will just get the plain text message back. So basically, the recipient uses its private key D, N to decrypt the message. Next, we move on to the analysis of the RSA algorithm. So when we have a capital number n, which is basically the product of two prime numbers p and q, like let it be a n bit sized number where n is a small n. So the time complexity for generating the prime numbers will be O of n power 4. So like the complexity is O of n power 4 just because we use Miller-Rabin test to test whether a given number is a prime number or not. So the time complexity for that is O of n power 4. Next, we multiply the two prime numbers p and q. The time complexity is O of n square. So the time complexity is O of n square just because we are considering elementary multiplication. Although there are different multiplication techniques, algorithms such as Karatsuba's algorithm, which will bring down the complexity to n to the power 1.58, or even if fast Fourier transform is used, then it can be even brought down to n log f. But for the sake of simplicity, we'll be sticking to the elementary multiplication. Now the time complexity for generating a relative prime number e is O of n cube. Then the time complexity for calculating modular inverse to get t is O of n cube. Now, like since the encryption process involves the modular exponentiation process, so it will have the time complexity of O of n cube. And similarly, the decryption process, which also uses the modular exponentiation, will have a time complexity of O of n cube. Now let's move on to encrypting large text files using RSA. So basically, when we require to have secure file transfers, so we cannot just directly encrypt that large text file using RSA, because like RSA works on data size comparable to the size of the keys. So it won't work with very large text file. So the first step will be to generate a random symmetric key. Now we will encrypt the text file using the chosen symmetric algorithm. So we'll choose a symmetric algorithm. Let's say we choose AES, which stands for Advanced Encryption Scheme. We'll use that algorithm for like encrypting the text file, and we'll be using the symmetric key for encrypting it. Alongside this encryption, alongside this symmetric algorithm. Now we will encrypt the symmetric key using RSA. So basically, we will just encrypt the symmetric key which we have using the recipient's RSA public key. We will just encrypt that symmetric key. Now, further, what we will do is we will just transmit the encrypted data along with the key to the recipient. Now, the recipient will decrypt the symmetric key with RSA because with their own RSA private key, because like their public key was only used for encrypting this symmetric key, so they can just use their own private key to just decrypt this symmetric key. As soon as they decrypt the symmetric key, they can just decrypt the entire text file using the same symmetric algorithm which they initially used for encrypting the text file. So the algorithm I'm talking about might be AES if we have earlier used that algorithm for encrypting the text file. And this is how a very large text file is encrypted using RSA. So basically, we are using two techniques in conjunction. One is the RSA, and other is the symmetric algorithm for encryption. Okay, now let's move on to one of the most important practical application of RSA, where it is used for in digital certificates. So the first step is key generation. So the sender or the signer will just generate a public and the private key. Then the next step will they'll just create the digital signature for the data they have. So the first step in creating the digital signature is hashing. So they will use some hash function. Let's say SHA-256, which is one of the popular hash functions. So they'll get some hash value for the entire data. Now the hash function is chosen in such a way that even a small modification to the data will lead to a different hash value. Okay. Then what the sender will do, they'll just encrypt this hash value using their own private key this time, and will attach it to the data, and it will just distribute the signed message to the receiver. Now, when the receiver receives the this data along with the certificate, their first task will be to like verify this digital signature. So their first step will be hashing. They'll just like use the same hash function which was used by the sender, and they will just use the same hash function to get the data, and they'll get I'm sorry, they'll use this hash function on the encrypted data to get some hash value. Now, their next step will be they'll just try to decrypt the signature of like which is present on the data using the signer's public key. So they'll just decrypt this data using the signer's public key, and they'll again get some hash value. If both the hash values map or are equal to each other, then it means that the signature is valid and that the data has not been tampered in between. So this is how RSA is used in digital certificates. Moving on to another popular implementation of RSA, that is in SSL or TLS protocols. So we have a client and a server in SSL. So the very first step is establishing connection. Now, let's say the connection has been established between the client and the server after the three-way handshake. Let's say that connection has been established. After the connection has been established, the server will send a certificate, a server certificate to the client, but this certificate will also be having the server's public key. So now the client will first it will just verify the server certificate, like we'll check the cryptographic parameters. After verifying it, what it will do is it will just create a random pre-master secret key and will encrypt this key using the public key which was sent by the server. After the key has been encrypted, the key will be sent to the server. Now, as soon as the server receives that pre-master secret key, it will first like verify the client certificate if required, and the next step is it will just decrypt it using its own private key, because like it was encrypted only using the server's public key only. So the server can just use their private key to decrypt it. Once it is decrypted, now both the client and the server are sharing the pre-master secret key, and they can keep on using this key for encrypting and decrypting the message. So basically, over here also the two, the symmetric and the asymmetric encryption techniques have been used in conjunction, because the finally client and the server both have the shared symmetric keys. And as soon as both of them have shared symmetric keys, uh, in other words, we can say they have a secure communication. So they can exchange messages which are encrypted with the shared secret key. Next, we'll talk about the potential threats to RSA crypto system. So basically, the very basic idea of the very basic threat to RSA is factoring. If very large composite numbers can be factored into their prime factors, RSA will be broken. But like it is like, but this task is somewhat computationally infeasible. But with the advancement of quantum computing, there's an algorithm called the Shor's algorithm, which can break RSA by factoring large composite numbers into their prime factors. So let's talk more about the Shor's algorithm. So the Shor's algorithm is a quantum algorithm designed to like efficiently factor large numbers, and it was developed by Peter Shor in 1994. So it basically takes advantage of the unique properties of quantum computing, specifically the ability of qubits to exist in multiple states simultaneously, and also enabling parallel processing of information. So if implemented, like if the Shor's algorithm is implemented on a sufficiently powerful quantum computer, then Shor's algorithm could potentially factor large composite number into RSA. Like they can just factor large composite number into their prime factors, and they'll just do this in a polynomial time. So like this will like effectively result in RSA being broken. But it's also true and also essential to note that while the threat to Shor's algorithm is real, current quantum computing technology is not yet advanced enough to execute the algorithm against the large numbers used in modern RSA encryption. But however, like researchers and cryptographers like are already exploring post-quantum cryptography solution to prepare for a future like where quantum computing becomes more widespread and powerful. So let's finally move on to conclusion. So the first thing is we conclude is enduring impact of RSA. So the RSA public key crypto system like has revolutionized digital security and has been providing robust and efficient solution for key exchange, encryption, decryption, and digital signatures in various applications. Then we have seen diverse applications of RSA, like RSA's versatility, like as a public key crypto system, like has led to widespread adoption in various applications such as secure data transmission, authentication, digital signatures, SSL TLS protocols, which we just talked about. Uh, Next, we'll talk about like quantum computing challenges. It's also like with the advent of quantum computing and Shor's algorithm, which we just now saw, like it presents like really potential threats to like RSA and like other public crypto systems. Then let's talk a bit about like post quantum cryptography. So like in response to this like quantum computing challenges, like ongoing research in post quantum cryptography, like they basically aim to develop cryptographic algorithms which are resistant to like these quantum attacks, so that like the security of this digital infrastructure can be ensured for a longer period of time. Further, and lastly, we have like we will just talk about the future of digital security. So like as we like navigated like an increasingly interconnected world, and understanding and implementing strong cryptographic solutions like RSA remain essential for like maintaining privacy, security, and trust. So in a way, we can say that staying informed about advances in cryptography and potential threats to like RSA like helps us adapt in the ever evolving landscape of digital security. These are our references for our project, and thank you so much for listening.